Okay, before we do this inquiry question, we need to make a derivation here. So we're going to imagine this is a bird's eye view of like a round like dirt track. And there's a car on this dirt track just going around the track really fast. And we want to figure out at what velocity can a person go around this track and not slide off? Not slide off. What's the critical velocity the maximum velocity the car could go around this track and not slide off? So to do that, we need to do an FBD. We need to like maybe just cut across here, do a cross section of the track. So here's the car, driving around the track. Okay, and so there's an FBD on this. There would be mg down, right, the weight of the car. There would be a force going up that the track would be pushing up on the car. That's a normal force. And then what other forces do we have? Well, if this car is going around here really fast, there's a tendency for it to, to try to fly outwards, right? To fly off the track. So why wouldn't it? Well, it will eventually, as long as the grip of the tires and the rubber and the road, that friction is allowing it to continue to turn and go around the track. So once it goes fast enough velocity so that friction's overcome, then it's going to fly outwards. So there's a centripetal force working inwards, going like this. Okay, that is Fc. That's centripetal force. Now that centripetal force is actually equal. I'm going to do a derivation here. That centripetal force is actually equal to the friction. The friction is what provides the centripetal force that holds the car on the road and holds it in its circular path. So what is centripetal force? It's mv squared over r. And what's friction? Friction is mu normal force. And what's normal force? In this problem, normal force is mg. So mu mg. Masses cancel. V equals the square root of gur mu. So here is an equation. We just derived an equation for the critical velocity around a flat track. It could be asphalt, it could be gravel, whatever, but it's flat. It's a flat track. You can go faster if you increase the radius, right? So if you do a bigger track, you can actually go faster around a bigger track without flying off. Or you can go around the same track faster if your mu is higher. So if you have a better traction with the wheels in the road, you can actually go faster around the track as long as your mu is a little bit higher also. So this is the critical velocity for going around a track, square root of gur mu. All right, so the problem here is, what is the smallest radius in which you can turn a car if you are moving 65 miles per hour and the coefficient of friction between the tires and the road is 0.330. Okay, we're looking for the radius. So I'm going to square both sides. V squared equals gur mu. And then the radius would equal V squared divided by gravity divided by mu. Now, what is the velocity? The velocity needs to be in meters per second, and right now it's not in that. It's at 65 miles per hour. So we need to convert that real quick. 1 mile per hour is 0.447. So if I take 65 times 0.447, I get like 29 meters per second. So that's going to be 29 squared divided by 9.81. Also divided by, what was mu? Mu was 0.33. Okay? So I'm going to square that. I'm going to divide it by 9.81. I'm also going to divide it by 0.33. And I should get a radius of like 261 meters would be the radius. Remember, you had to have the velocity in meters per second, otherwise this radius wouldn't end up in meters the way we want it. So that should be the answer to that.